Welcome back to the deep dive. I have to be honest with you, right up front, reading through today's source material gave me a bit of an existential crisis about the internet.
That is a completely normal reaction. In fact, if you don't feel a little bit uneasy after reading about network security, you probably didn't read it closely enough.
Fair point. We usually think of cybersecurity as this high-tech digital warfare happening, out in the cloud. But today, we are zooming in on something much more physical.
We are.
We're talking about the wires in the wall, the jack under your desk, the soft underbelly of the network.
It's a classic problem. We spend millions building these massive digital fortresses, firewalls, intrusion detection systems, VPNs to keep the bad guys out.
Right.
But we rarely stop to ask, what happens if the call is coming from inside the house?
Exactly. We're diving into a stack of documents focused on network security fundamentals, with a heavy focus on a guide titled M10 Network Hardening Wire to User. And the visual that stuck with me is this idea of the castle. You have the moat, the drawbridge, the archers. That's your perimeter. But the argument here is that once you get past all that, the inside of the castle is just open.
It's surprisingly open. Historically, networks were designed for trust.
Yeah.
If you were close enough to plug a cable into a switch, the network just assumed you belonged there.
It didn't ask for ID.
Didn't ask for ID, just gave you a dial tone.
Which sounds incredibly naive in 2026.
It is. But that architecture is still the backbone of most local area networks, or LANs. That's what we call layer 2, and that is where the battle is actually lost most of the time.
Okay, so before we get into the mechanics of how things break, let's look at the stakes. The source material includes a slide called the Modern Threat Landscape.
Right.
And it's not just teenagers defacing websites anymore. It lists zombies and botnets.
It sounds like a B-movie, doesn't it?
It really does. But then you see the other categories. You've got DDoS distributed denial of service, where those zombies flood a target. You got the classic data breach. But the one that actually made me shudder was the screenshot of the ransomware.
The red screen.
Yeah. Oops, your files have been encrypted. It's so polite, yet so aggressive. And it demands, what, $300 in Bitcoin with a countdown timer? It feels visceral.
That's the psychological element. Ransomware stops your business cold. But here's the thing people miss. How did that ransomware get there?
Right.
Everyone assumes some elite hacker cracked the firewall code.
Like in the movies, typing furiously against a green screen.
But the stats in our reading tell a different, much more boring story. It says 95% of attacks start with spear phishing.
95%. So someone just clicked a link.
Someone inside the castle lowered the drawbridge. Maybe they thought they were opening a FedEx tracking link, but they actually downloaded a payload. And once that payload is on a laptop inside the network, the firewall, that millions of dollars of perimeter defense, is now looking in the wrong direction.
It's looking outward.
The threat is behind it.
And this is where the soft underbelly comes in. The attacker is now on the trusted LAN.
Precisely.
Yeah.
And this is where we have to talk about the OSI model. I know eyes usually glaze over when we talk about the 7 layers of networking, but stick with me.
Okay, the diagram shows layer 7 at the top. That's the application, like your web browser. And layer 1 is the physical wire. Layer 2 is the data link.
Think of layer 2 as the road system in a city. Layer 3 is your GPS telling you where to go. Layer 7 is the destination, the bank, the store, the house.
The source material has a rule written in big red text. If layer 2 is compromised, layers 3 through 7 are defenseless.
Because if I control the road, your GPS doesn't matter.
Oh, wow.
I can change the street signs. I can detour you into a dark alley. I can pave over the road entirely. If the foundation layer 2 is rotten, it doesn't matter how secure the bank vault at layer 7 is. I'm hijacking the armored car before it even gets there.
That is a terrifying thought. So the goal of this network hardening is basically to put checkpoints on those roads.
Correct. We need to stop assuming that just because a car is on the road, it's allowed to drive there.
So the sources introduced the AAA framework as the solution for this. And I have to say, the analogy they used finally made this click for me.
The credit card one.
Yeah, they compare network security to a credit card.
It's the standard analogy for a reason. It works perfectly to explain identity and control.
Okay, so let's break it down. The first A is authentication. In the credit card world, this is the card itself and your PIN in.
Right. It answers the question, who are you? You claim to be John Doe. Prove it. Here's the card. Here's the secret code.
Then the second A is authorization.
And this is the crucial step that people forget. Just because you are John Doe and the bank knows it doesn't mean you can buy a private jet.
You have a credit limit.
You have a credit limit. Maybe it's $1,500.
So on a network, authentication is you're allowed to log in, But authorization is you can only access the printer and the internet, not the HR payroll server.
Exactly. It's the least privileged principle.
And the third A is accounting.
The monthly bank statement. What did you do? If $500 goes missing, we need a paper trail to see where it went. In networking, these are the logs.
Oh.
Without accounting, you have no forensics when things go wrong.
So that's the theory. But how does a switch, a piece of hardware, actually do this? The reading talks about 802.1x.
This is the implementation. And let's keep the credit card analogy going because it gets a little technical here. In 802.1x, you have 3 players. First, the supplicant.
That's the client, right? My laptop.
Right. Your laptop is the customer holding the credit card. It wants to buy something, in this case, network access.
Then you have the authenticator. This is the switch.
The switch is the card reader at the register.
Yeah.
Now, does the card reader know how much money you have in your bank account?
No, it's just a machine.
Exactly. It's dumb. It just reads the data and passes it along. It passes it to the third player, the authentication server.
The bank.
The bank. The server checks its database, verifies the PIN, checks the credit limit, and sends a message back to the switch saying approved or declined.
And if it's approved.
The switch opens the port, literally turns the power on for that data lane. If it's declined, the port stays dead.
So that's the bouncer at the door. That sounds secure.
It is secure if you implement it.
But, and there's always a but in these documents, what if the attacker doesn't try to use a fake ID? What if they just try to break the door down or trick the bouncer?
This brings us to the attack toolkit. And honestly, this is where the reading gets a little scary because these tools are not expensive.
No?
They're free. They are built into Linux distributions that anyone can download.
Okay, let's talk about the first one, MEE address table flooding. The tool is called MacOff. The source says it can blast 8,000 bogus frames per second at a switch.
An incredible number. So every switch has a brain and memory table called the ME address table. It learns where everyone sits.
Bob is on port 1, Alice is on port 2.
Exactly. That way, when Bob emails Alice, the switch sends the data only to port 2. It's private, but that memory is finite. It's like a small whiteboard. What MacOff does is scream 8,000 fake names a second at the switch. I'm Steve. I'm Dave. I'm X. I'm Y.
And the switch tries to write them all down.
It tries. And within seconds, the whiteboard is full.
So what happens when the brain is full? Does the switch just shut down?
See, that would be the secure thing to do. But in the world of networking, availability is often prioritized over security. So it doesn't shut down.
It fails open.
It enters fail-open mode. It turns into a hub.
A hub? What's a hub?
A hub is an old, dumb device that just shouts everything to everyone. Because the switch can't look up where Alice is anymore, it panics and sends Alice's email to every single port on the device.
Wow. So the attacker, just by making noise, forces the switch to hand over everyone else's data.
Yes, they can now sit there and sniff every packet. Passwords, emails, files, it's all streaming right to them.
That seems like a massive design flaw.
It is. It's because the alternative is the network stops working. And historically, network engineers would rather be insecure than have the phone ring because the internet is down.
Wild. So how do we fix it?
Port security. It's a feature where you tell the switch, hey, look at this port. I expect one laptop to be plugged in here, maybe a phone too. So if you see more than 2 MSC addresses coming from this hole in the wall, kill it.
Cut the line.
Immediately. The attack stops before the table even fills up.
Okay, that makes sense. Let's move to the next one, which feels even more devious. DHCP starvation and spoofing.
This is a 2-part attack. DHCP is the protocol that assigns IP addresses. It's the take-a-ticket machine at the deli counter.
You need an IP to get service.
You do.
Yeah.
So starvation is when the attacker runs a script that just grabs every single ticket. They request 500 IPs in a second.
So when I walk in with my legitimate laptop and ask for an IP,
the server says, sorry, we're out. You get nothing. You get that weird 169.254 address that means you're disconnected.
right.
It's a denial of service.
But the spoofing part involves a rogue server. This is the man-in-the-middle setup.
Right. So the legitimate server is out of tickets, or maybe it's just a little slow. The attacker sets up their own DHCP server on their laptop. When your computer shouts, I need an IP, the attacker shouts back, here you go.
The fake valet.
The fake valet. He takes your keys, he gives you a spot, but he also tells you, hey, the exit is that way. He assigns himself as the default gateway.
And the gateway is the way out to the internet.
Exactly. So now every time you Google something or log into your bank, your traffic goes to the attacker's laptop first. He inspects it, maybe copies it, and then forwards it to the real router so you don't even notice anything is wrong.
It's invisible.
Completely, unless you're looking for it.
So how do we stop the fake valet?
DHCP snooping. We configure the switch to identify trusted ports. We say, the real DHCP server lives on port 24, the uplink to the core. If a DHCP offer comes from port 5, the port under your desk, the switch treats it like poison.
It just drops it.
It drops the packet.
Yeah.
You are not authorized to hand out tickets.
I want to talk about VLAN hopping. The concept of a virtual LAN is to separate traffic. Right. HR is on VLAN 10, guests are on VLAN 20. They shouldn't be able to talk.
Correct. It's logical separation on the same physical wire.
But the attack mentions switch spoofing and double tagging. To understand this, I think we need to explain what a trunk is first.
Good point. A normal port, an access port, belongs to one VLAN. Your desk is in HR. But the cable connecting two switches together needs to carry traffic for everyone. HR, engineering, guests. That multi-lane highway is called a trunk.
So the trunk is the master key. It carries everything.
Yes. Now, in the old days, switches were configured to be helpful. If you plugged in and said, hey, I'd like to be a trunk, the switch would say, sure thing, let's negotiate.
Just believes you.
It's called DTP Dynamic Trunking Protocol. It wants to make setup easy. So an attacker plugs in, runs a script to say, I am a switch, and boom, they have a trunk link. They can now see traffic for every VLAN in the company.
That is absurdly easy. Yeah. And double tagging? What's that?
That's the Trojan horse. VLANs work by putting a tag or a sticker on the data packet. This is for VLAN 10. Double tagging is when the attacker puts a sticker for VLAN 10 on the outside, but hides a sticker for VLAN 20 underneath it.
Like smuggling.
Exactly. The first switch strips off the outer sticker, sees the inner sticker, and unknowingly passes the packet into the secure area.
Gain the fix.
Stop the negotiation, disable DTP, hardcode your ports. Tell the switch you are an access port and you will never be a trunk, no matter how nicely the other device asks.
It seems like the theme here is stop the switch from being so polite.
That is basically the definition of network hardening. Network protocols are polite by default. Security requires them to be suspicious.
Speaking of polite, let's talk about ARP spoofing. The source mentions gratuitous ARP, which sounds like a gift you didn't ask for.
It is exactly that. ARP is the protocol that maps an IP address to a physical device. It asks, who has IP 10 by 1 by 1 plot 1, and the owner replies.
Simple enough.
But gratuitous ARP is when a device just shouts out, hey everyone, just an update. I am now the router. Please send all traffic to me.
And the other computers just update their lists.
By default, yes. They're gullible.
Yes.
It's the Airbud rule. There's nothing in the rulebook that says a dog can't play basketball, and there's nothing in ARP that says a random laptop can't claim to be the router.
So it creates another man in the middle.
Precisely. And the fix, Dynamic ARP Inspection, DAI, relies on that DHCP snooping database we built earlier. It checks the claim. Wait, this guy on port 5 claims to be the router. My list says he's just a printer. Block him.
I love how these defenses layer on top of each other. You need the snooping to make the inspection work.
It's a defense matrix. You can't just pick one.
One last attack before we zoom out. STP manipulation. Spanning tree protocol prevents loops, right?
Yes. If you plug a cable into two ports on the same switch, you create a loop that can crash the network. STP prevents this by electing a root bridge, the king switch, that directs all the traffic.
The king switch.
The king is elected based on who has the lowest ID number. So an attacker plugs in a gaming PC, runs a tool to broadcast a message that says, I have a spectacularly low ID number. I should be king.
And the network bows down.
If you haven't secured it, yes. The network reconverges. Traffic starts flowing toward the attacker because they are now the root of the tree.
Which creates a massive bottleneck or allows them to intercept data.
Exactly. The fix is BPDU guard. It's a setting that says, if any device on this user port claims to be the king, cut its head off.
Brutal. I like it.
It shuts the port down instantly.
There's a section here on information leakage that mentions CDP reconnaissance. Cisco Discovery Protocol.
CDP is the loudmouth at the bar. It's very useful for admins because it broadcasts, hi, I am a Cisco switch model 3550 running iOS version 12.1 and my IP is this.
Useful for you, but also very useful for the hacker.
Exactly. If I know the exact iOS version, I can look up specific vulnerabilities for that software. I don't need to guess.
So tell the loudmouth to shut up.
Disable CDP on edge ports. Only let switches talk to other switches.
And finally, management hygiene. This feels like basic common sense, but the source makes a big deal out of it. Replace Telnet with SSH.
You would be shocked how many networks still run Telnet. Telnet sends everything in plain text. If you take your admin password and I'm on the line, I can just read your password.
Just like sending your banking info on a postcard.
It is, whereas SSH is an encrypted, sealed letter.
Right.
Always use SSH and HTTPS, never clear text.
So we've covered a lot of acronyms here. Port security, DHCP snooping, DAI, BPDU guard. It feels like a lot to configure.
It is, but remember, the defense matrix slide from the source, it simplifies it. Every attack has a specific counter move. You don't have to invent this stuff, you just have to turn it on.
The sources wrap this up with the 3 rings concept. Can you summarize that for us?
Sure, think of concentric circles. Ring 1 is infrastructure, that's everything we just discussed. Hardening the switch, locking down layer 2. Ring 2 is access control. That's the AAA and 802.1x. Checking IDs before letting people in. And ring 3 is the endpoint. That's the antivirus and firewalls on the laptop itself.
And the message is, you need all 3.
If you only have ring 3, your antivirus, but I own the network at ring 1, I can just block your antivirus from getting its updates. You need depth.
It really challenges the way we think about trust. We tend to trust things that are physically close to us. If a guy is sitting in the cubicle next to me, I assume he's an employee.
Right.
If a printer is in the hallway, I assume it's safe.
And that assumption is the vulnerability.
The source material leaves us with a final thought that I think will stick with me. It says, security is only as strong as the weakest link. In modern networks, that link is often the trusted LAN.
It really changes how you look at a wall jack, doesn't it?
It does. We sleep well at night because we bought the expensive firewall, we watch the digital border. But this deep dive suggests the real danger might be sitting in an empty conference room right now, plugging a $30 Raspberry Pi into a generic Ethernet port.
It's not just a plug. It's a direct line into the heart of the operation.
That is a terrifying note to end on, but a necessary one. Are you watching The Wire or just watching the wall?
A question for every admin to answer.
Thanks for joining us on this deep dive. Stay paranoid out there.
Stay secure.
See you next time.